Yellowstone supervolcano ancient eruptions? Where are the magma plumes? And where are the locations, and what is the temperature of the magma chamber? This explains why we have certain earthquake swarms, for example, west-northwest of the caldera in Montana, and also south-southwest in Utah. Yellowstone's ancient supervolcano, molten plume of material cooler than expected. The source of this research finding is the National Science Foundation. The geysers of Yellowstone National Park owe their existence to the Yellowstone hotspot, a region of molten rock buried deep beneath Yellowstone, as geologists have found. But how hot is this hotspot, and what's causing it? In an effort to find out, Derek Shute of Colorado State University and Ken Ducker of the University of Wyoming took the hotspot's temperature. The scientists published results of their research, funded by the National Science Foundation, the NSF, Division of Earth Sciences, in the August 2008 issue of journal Geology. Yellowstone, they say, is located atop of one of the few large volcanic hotspots on Earth, according to Shute. And he says, but though the hot material is a volcanic plume, it's cooler than others of its kind, such as one in Hawaii. That's another hotspot. When a supervolcano last erupted at this spot more than 600,000 years ago, its plume covered half of today's United States with volcanic ash. Details of the cause of Yellowstone supervolcanic periodic eruptions through history are still unknown. Thanks to new seismometers in the Yellowstone area, scientists are obtaining new data on the hotspot. Past research found that in rocks far beneath southern Idaho and northwest Wyoming, seismic energy from distant earthquakes slows down considerably. So using the recently deployed seismometers, Shute and Ducker modeled the effects of temperature and other processes that affect the speed at which seismic energy travels. They then used these models to make the estimate of Yellowstone's hotspot's temperature. They found that the hotspot is only 50 to 200 degrees Celsius hotter than its surroundings. Although Yellowstone sits above a plume of hot material coming up from deep within the earth, it's a remarkable lukewarm plume, said Shute, comparing Yellowstone to other plumes. Although the Yellowstone volcano's continued existence is likely due to the upwelling of this hot plume, the plume may have become disconnected from its heat source in Earth's core. Disconnected, however, does not mean extinct, said Shute. It would be a mistake to write off Yellowstone as a dead volcano. A hot plume, even a slightly cooler one, is still hot. Yellowstone's plumbing reveals the plume of hot and molten rock is 410 miles deep, according to the University of Utah. The most detailed seismic images yet published of the Yellowstone supervolcano's plumbing shows a plume of hot and molten rock rising from the northwest at a depth of at least 410 miles, contradicting claims that there is no deep plume. A related study indicated that the banana-shaped magma chamber a few miles beneath Yellowstone is 20% larger than believed, so a future cataclysmic eruption could be a lot larger than they thought. The most detailed seismic images yet published of the plumbing that feeds the Yellowstone supervolcano shows a plume is hot, molten rock rising at an angle from the northwest at a depth of at least 410 miles. Contradicting claims that there is no deep plume, only shallow hot rock moving like slowly boiling soup. A related University of Utah study used gravity measurements to indicate that the banana-shaped magma chamber of hot and molten rock a few miles beneath Yellowstone is 20% larger than previously thought, so a future cataclysmic eruption could be even larger than they believed. The study of Yellowstone's plume also suggests the same hotspot that feeds Yellowstone volcanism also triggered the Columbia River flood basalts that buried parts of Oregon, Washington State, and Idaho with lava starting 17 million years ago. So you see how all these hotspots that feed Yellowstone also triggered the other flood basalts. Those are key findings in 4 National Scientific Foundations funded studies in the latest issues of the Journal of Volcanology. Basically, they're all very close to each other. Let's not forget that Yellowstone is part of the subduction zone. Now, a lot of people say, no, it's too far. It's not part of the subduction zone. It is part of the subduction zone. Don't forget that Yellowstone is on the Rocky Mountains, and that's how the Rocky Mountains were formed by the subduction zone. The Farallon plate going under the North American plate. Now, the key findings in National Science Foundation funded studies in the latest issue Journal of Volcanology and Geothermal Research. The studies were led by Robert Smith, researcher, professor, and professor emeritus geophysics at the University of Utah, and coordinating scientist for the Yellowstone Volcano Observatory. Smith says, "We have a clear image using seismic waves from earthquakes, showing a mantle plume that extends from beneath Yellowstone. The plume angles downward 150 miles to the west-northwest of Yellowstone and reaches a depth of at least 410 miles," Smith says. The study estimates the plume is mostly hot rock, with 1% to 2% molten rock in sponge-like voids within the hot rock. Some researchers have doubted the existence of a mantle plume feeding Yellowstone, arguing instead that the area's volcanic and hydrothermal features are fed by convection, the boiling-like rising of hot rock and sinking of cooler rock from relatively shallow depths of only 185 to 250 miles. The hotspot, a deep plume, blobs, and shallow magma. Some 17 million years ago, this is before the eruptions before passing the border from Nevada to Idaho, some 17 million years ago, the Yellowstone hotspot was located beneath the Oregon-Idaho-Nevada border region. There you go. Feeding a plume of hot and molten rock that produces caldera eruptions, the biggest kind of volcanic eruption on Earth. As North America slid southwest over the hotspot, the plume generated more than 140 huge eruptions that produced a chain of giant craters, or calderas, extending from Oregon-Idaho-Nevada border northeast to the current site of Yellowstone National Park, where huge caldera eruptions happened 2.05 million years ago, 1.3 million years ago, and 642,000 years ago. These eruptions were 2,500, 280, and 1,000 times bigger, respectively, than the 1980 eruption of Mount St. Helens. The eruptions covered as much as half the continental United States, with inches to feet of volcanic ash. The Yellowstone caldera, 40 miles by 25 miles, is the remnant of the last giant eruption. The new study reinforces the view that the hot and partially molten rock feeding volcanic and geothermal activity at Yellowstone is not vertical, but has 3 components. The 45-mile wide plume that rises through Earth's upper mantle from at least 410 miles beneath the surface. The plume angles upward to the east-southeast until it reaches the colder rock of the North American crustal plate, and flattens out like a 300-mile wide pancake about 50 miles beneath Yellowstone. The plume includes several wider blobs at depths of 355 miles, 310 miles, and 265 miles. And this conduit is not one tube of constant thickness, says Smith. It varies with width at various depths, and we call those things blobs. A little understood zone between 50 miles and 10 miles deep, in which blobs of hot and partially molten rock break off the flattened top of the plume and slowly rise to feed the magma reservoir directly beneath Yellowstone National Park. The magma reservoir, 3.7 miles to 10 miles beneath the Yellowstone caldera. The reservoir is mostly sponge-like hot rock with spaces filled with molten rock. It looks like it's up to 8% or 15% melt, says Smith, and that is a lot. That's a lot, he says. Researchers previously believed that magma chamber measured roughly 6 to 15 miles from southwest to northwest and 20 or 25 miles from southwest to northeast, but new measurements indicate the reservoir extends at least another 13 miles outside the caldera's northeast boundary, Smith explains. He says the gravity and other data show the magma body, quote, is an elongated structure that looks like a banana with the ends up. It is a lot larger than we thought. I would say about 20% by volume. This would argue there might be a larger magma source available for a future eruption, end quote. Images of the magma reservoir were made based on the strength of Earth's gravity at various points in Yellowstone. Hot and molten rock is less dense than cold rock, so the tug of gravity is measurably lower above the magma reservoirs. The Yellowstone caldera, like other calderas on Earth, huffs upward and puffs downward repeatedly over the ages, usually without erupting. Since 2004, the caldera floor has been rising 3 inches per year, suggesting a recharge of the magma body beneath it. How to view a plume. Seismic imaging using earthquake waves that travel through the earth and are recorded by seismometers. Wave travels more slowly through hotter rock and more quickly in cooler rock, just as X-rays are combined to make CT scan images of features in the human body. Seismic waves data are melded to produce images of Earth's interior. The study, the Yellowstone Geodynamic Project, was conducted during 1999-2005, and it used the average of 160 temporary and permanent seismic stations and as many as 200 to detect waves from some 800 earthquakes, with the stations placed 10 miles to 22 miles apart, closer than other networks and better able to see, quote-unquote, underground, and some 160 global positioning system stations measured crustal movements. By integrating seismic and GPS data, it's like a lens that made the upper 125 miles much clearer and allowed us to see deeper, down to 410 miles, Smith said. The study also shows a warm clock, not as hot as the plume, stretching down from Yellowstone southwest under the Snake River Plain. That's the river just southwest of Yellowstone. The Snake River Plain at depths of 20 miles to 60 miles. The rock is still warm from eruptions before the hotspot reached Yellowstone. Can you imagine? The ground is still hot from those eruptions. A plume blowing in the 2-inch per year mantle wind. Seismic imaging shows a slow zone from the top of the plume, which is 50 miles deep, straight down to about 155 miles. But then, as you travel down the plume, it tilts to the northwest as it dives to a depth of 410 miles, Smith says. That is the base of the global transition zone from 250 miles to 410 miles deep. That is the boundary between the upper and the lower mantle, the layers between Earth's crust. At that depth, the plume is about 410 miles beneath the town of Wisdom, Montana, which is 150 miles west-northwest of Yellowstone. That's that's the area where we're having our quake swarms lately. That's the area, 150 miles, that's around Helena, Montana. that's, we've been having them for weeks there. So, it's that plume there's a plume there. Smith says, it would not surprise me if the plume extends even deeper, perhaps originating from the core mantle boundary, some 1,800 miles deep. Now, why does not the plume rise straight upward? This plume material wants to come up vertically. It wants to buoyantly rise, says Smith, but it gets caught in the wind, quote unquote, of the upper mantle flow, like smoke rising in the breeze, except in this case the breeze of slowly flowing upper mantle rock is moving horizontally 2 inches per year. While the crustal plate moves southwest, the warm underlying mantle slowly boils down to the convection, with warm areas moving upwards and cooler areas downwards. Northwest of Yellowstone, this convection is such that the plume is blown east-southeast by mantle convection, so it angles upward towards Yellowstone. Scientists have debated for years whether Yellowstone's volcanism is fed by a plume rising from deep in the earth or by shallow churning in the upper mantle caused by movements of the overlying crust. Smith says the new study has produced the most detailed image of the Yellowstone plume yet published. But a preliminary study and other researchers suggest Yellowstone plume goes deeper than 410 miles, ballooning below that depth into a wider zone of hot rock that extends at least 620 miles deep. The notion that a deep plume feeds Yellowstone got more support from a study published indicating that the Hawaiian hotspot, which created the Hawaiian Islands, is fed by a plume that extends downward at least 930 miles, tilting southeast. A common source for Yellowstone and the Columbia River basalts? Based on how the Yellowstone plume slants down, Smith and colleagues projected a map where the plume might have originated at depth when the hotspot was erupting at the Oregon-Idaho-Nevada border area from 17 million to almost 12 million years ago. They saw overlap between the zones within the Earth where eruptions originated near the Oregon-Idaho-Nevada border and where the famed Columbia River basalt eruptions originated when they were most vigorous, 17 million to 14 million years ago. Their conclusion: the Yellowstone hotspot plume might have fed those gigantic lava eruptions which covered much of the eastern Oregon and eastern Washington state. Yeah, the Yellowstone hotspot plume might have fed those gigantic lava eruptions. I argue it is the common source, says Smith. It's neat stuff and it fits together. Smith conducted the seismic study with 6 University of Utah present or former geophysicists, former postdoctoral researchers Michael Jordan of SINTF Petroleum Research in Norway and Stephen Husen of Swiss Federal Institute of Technology. He conducted the gravity study with the former University of Utah graduate student Katrina De Nosacco and Tony Laurie of Utah State University in Logan. Okay, so this is from the University of Utah and it's on Science Daily. At least now we know why we have those quake swarms near Helena, Montana. That's where another plume is located. From plume of the Yellowstone supervolcano. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.